morning. So today I will continue with the lectures. The idea today is to talk about anomalies, in particular about the axial anomalies. And as I was telling you on Monday, anomalies are a classical symmetry that is broken at the quantum level. Okay? So perhaps one of the first examples of this was the axial anomaly. It was computed perturbatively by Adler, Bell, and Jacob at the end of the 60s. But then Fujikawa, at the end of the 70s and beginning of 80s, computed this completely non-perturbative. So today I would like to present the computation of Fujikawa, and this will be related with the talk of that I gave on Monday, because some particular configurations that induces the anomaly are instantons in general and configurations with non-trivial topology. So this will be sort of an application of the configuration that we talk about on Monday. Okay? So let us start by defining the Dirac action, Minkowski space, and let us talk about the global symmetries of the Dirac action. Okay? So they will be the axial anomaly. So this was done by Adler, 69, Bell, also 69, and then, like 10 years later, was done by Fujikawa. Okay? And I will focus mainly on the computation of Fujikawa, of this guy. So let us write the Dirac action. The Dirac action in Minkowski space. So the Dirac action will be for dimensional Minkowski space. It will be this. Let's put it in this way. Psi. And people often call this operator this slash. Okay? And I think that Breno was explaining to you what these gamma matrices are. So the gamma matrices, let us put it here. Where gamma are the Dirac gamma matrices, and they satisfy the Clifford algebra. Okay, and the Clifford algebra is given by the anticommutator of these guys. This gives you 2 times eta mu nu and identity 4 times 4 identity matrix. Okay? Additionally, this guy is called the adjoint Dirac spinor that can be defined considering the gamma 0. So psi bar is the adjoint Dirac spinor. And what else? And there are some hermeticity properties of these gamma matrices that can be summarized in the following way. So gamma mu dagger is gamma 0, gamma mu, gamma 0. So if you take from here the 0, 0 components, then you get on the right hand side the 0, 0 components of the Minkowski metric. I'm considering now the mostly minus signature. So this implies that gamma 0 squared is minus 1. And therefore, you can see that gamma 0 is anti-Hermitian. And for mu being spatial indices, then those matrices are Hermitian in this case. Okay. Additionally, the other way around, it all D. We can define the chiral gamma matrix by taking the product of all the gamma matrices, like gamma 0, 1, 2, and 3. And this allows us to define what will be called the chiral gamma matrix, gamma 5, and this will be gamma 0, gamma 1, gamma 2, and gamma 3. An important property of this gamma 5 is that anti-commutes with all the other gammas. So we have this property. And what else? And this is it. And it is Hermitian. So if you give it the definition of taking the dagger, this will give you exactly the same matrix, okay? Okay, with these ingredients in mind, let us analyze the symmetries of the Dirac action, okay? And there are two kinds of symmetries that we can discuss. Both of them are U1 symmetries, but one is vectorial and the other one is axial, okay? So we have, let's say, the global symmetries. So if you take these spinors, these Dirac spinors, and perform the following transformations, namely, I will call this U1 vector symmetry that takes the spinor and gives you E adds a phase to the Dirac spinor, and the other way around with the adjoint Dirac spinor prime. This will give you psi dagger minus I alpha. With this, alpha is just a real parameter, and you plug it here, you will see that the action remains invariant. Okay? But there is another one, which is the chiral or the axial U1 symmetry, that it is sort of the same of this one, but adding here a chiral gamma matrix. Okay, so if you consider that, and you take the Dirac spinor and perform this U1 axial transformation, I will put another parameter, call it beta gamma 5 psi. And notice that since the adjoint Dirac operator involves a gamma 0, and here I have a gamma 5, that anticommutes with all the gammas, the adjoint Dirac spinor will transform in this way. Will give you psi bar e to the plus e beta gamma phi. You can convince yourself by taking this one, taking that joint, considering that you have a gamma 0 here, and that gamma 0 with gamma 5 anticommutes, and so this will give you a plus here instead of a minus. This sign is important in what follows, so I'm emphasizing this point now. And you take these two, and it's easy to convince yourself that applying these two transformations into the Dirac action, then the Dirac action will remain invalid, okay? And we know, due to the Nether theorem, that this implies a conservation law. Two conservation laws, actually, because we have two different U1 symmetries at this level. So the Nether current the Nether currents are, so associated to the first one, this is the standard electric current that you know from electromagnetism. So the first one will be T mu, J mu equal to 0, but there is another one associated to the U1 axial symmetry, and this implies that the axial current will be conserved, where this J mu is I psi bar gamma mu psi, and the axial current will be J mu 5 I psi bar mu gamma 5 psi. Okay? These are the two currents which are conserved in this case. And every time we have a conservation law of this form, we can compute conserved charges. And this is sort of, if, let's say, and even in curved spacetimes. So I will consider now the covariant derivative that transforms covariantly under general coordinate transformation. So if you have this kind of law, so you can integrate both sides in a volume. Let's say in a volume, d for x square root of g. And then what happens here is that, so we have a 0 on the left hand side, and this will be on the volume, d for x square root of g, and this one, and you can use the Stokes theorem to write this in the following way, like dm, let's say d3x square root of h, where h is the induced metric on this boundary. You have a normal vector to this boundary, and then j mu. So it is sort of the covariant version of the divergence theorem that you learn in calculus. So this is the, let's say, this is B, the boundary will be dB, and here we have n, that will be n mu. Okay? But actually you can consider that the boundary can be the union of two open surfaces, like, let's say I will separate dB, sorry, I put here dm, but this is dB. So let us consider that this can be the union of dB1 dB1 union dB2, and I will put dB1 will be the upper hemisphere of this boundary, and then dB2, and so dB is the union of the two. So I can separate the right hand side, and this will give me, so before separating, there is a more convenient notation for this, which is this one, J mu sigma mu, where this is the oriented area element, and it is just, you can read it from here, right? So it is this piece will be the sigma mu, okay? But it is shorter, so I will use that one. And the idea is that you can separate these by considering that the boundary is divided in two. So in such a case, the integral will be dB1 J mu, the sigma mu, but associated to the, let's say, to the upper hemisphere, dB1 plus dB2 J mu, the sigma mu 2, okay? And this is equal to 0. So you can see that actually one integral in one hypersurface is equal up to a orientation to the other one. So this means at the end of the day that if you have this kind of conservation law, then it implies that if this integral doesn't depend on the boundary that you are choosing. So I can define, or we can define conserved quantity which doesn't depend on the choice of of your hypersurface. And so in this case, I will define it in like over, let's say, sigma, which is a codimension 1 hypersurface in this case, and this will be d3x square root of h and mu j, okay? And so I can associate now a conserved quantity to these two currents in this case. And it is customary to assume that sigma is a Cauchy hypersurface. This means that it is crossed only once by a time-like curve. So then we have a conserved quantity for B, A. Namely, let's say sigma d3x square root of h and mu j mu, and associated to the axial one, d3x square root of h and mu j mu 5. So, and the standard choice for sigma is, as I was saying, a Cauchy hypersurface. So let us choose sigma to be for G hypersurface. So this means that if I have here sigma, it is like the differential geometry analog of a picture, of a photo, in an instant of time t. It is crossed only once by a time-like curve. So the normal vector to this curve is time-like. This will be, let's say, n. That will be n mu. N mu, but this time-like. So that means that n times n can be normalized such that it is equal to -1. Okay? If this is the case, then n, I can always choose coordinates such that n has only time-like components, and therefore we can write this QB as v3x square root of h and 0, j0, and the other one, the axial, the same thing, okay? v3x square root of h and 0, j0, 5. So let us see what the temporal components of the conserved currents are, because it will be clear what they represent. But perhaps you know from your electrodynamics courses that this will give you the electric charge, but that is associated to the U1 axial symmetry, a conserved quantity that is related to something a bit different. Okay? Is there any questions so far?
How do you choose in how many subspaces to secure the?
You can choose as many as you want, as long as the union is a closed surface. In this case.
Yes, quantity. Mu, J mu.
Which one? This?
Answer.
This one?
No. It's J mu S or J mu.
Sorry, this is J mu 5. I have a terrible handwriting, so yeah, it is 5. 5? 5, it is related with this guy, which is, because you have a gamma 5 here, so this is sort of this is the axial current, and this is the vectorial current, let's say. So this transforms as a vector, and the other one as a pseudo vector. Okay? Any other question?
The conserved quantity is it would be because if it's the same at the two Cauchy surfaces, that means that the conserved quantity is in whichever.
Yes, exactly.
Cauchy surface.
So, excellent point. So if I have a hypersurface, a Cauchy hypersurface of initial data, and I compute this quantity there, and then I evolve the system to another one. Let's say here. So this will be sigma T1, and this will be sigma T2. And you compute this integral in the first Cauchy hypersurface, and then you evolve the system and compute the same, like, I don't know, 10 minutes later. The value of these guys will be the same. Is the idea. All right. So let us see what these components are. Okay. So I have the impression that Breno talked about the bile spinners. Did he? Okay. So in the bile basis, we can choose a particular representation for gamma 5 that is super useful, and also for the spinners. So in the bile basis, gamma 5 can be represented as a 4 times 4 matrix, where here you have the identity 2 times 2 minus the identity 2 times 2, 0, 0. And also you can decompose the Dirac spinner into 2 components, bile spinners, that can be represented like with the plus and with the minus. Okay? So using this notation, we can see that the components, because recall that the conserved currents are these ones. So I will compute the 0 components of these 2 currents, okay? Using the bile basis. The conserved actually the temporal components of the conserved currents are. Let us work the first one. So J0 would be I gamma 0 psi, right? So, but the Dirac adjoint was I, so I will have I squared psi dagger gamma 0 gamma 0. This gamma 0 comes from the definition of the adjoint. The other gamma 0 is this one, and then I have the Dirac adjoint. But recall, as I was saying, we had this one, right? So from the Clifford algebra to eta mu 1, where we are using the correct signature for this metric, which is diagonal minus plus plus plus. So if you take now gamma 0 squared, take 0, 0 here, so this will be gamma 0 plus gamma 0, gamma 0. So this is 2 times gamma 0 squared. And on the right hand side, I will have 2 times minus the identity. Minus 1, 2 times the identity. So this means that gamma 0 squared will be minus the identity. Okay? I will use this here. So this will be minus the identity, 4 times 4. This is another minus 1. And using the bile basis for the Dirac spinners, you will see that this is psi dagger, so this is a dagger, plus psi plus, plus psi dagger minus psi minus. Okay? This is chi, actually, not psi. And this is a dagger. Okay, what about the other one? So if we compute the temporal components for the axial current, we will have I psi bar gamma 0 gamma 5 psi. And it is exactly the same thing, but with the gamma 5 here. So this will be dagger gamma 0 gamma 0 gamma 5 psi. And again, this is equal to minus 1. This is minus 1. And this look pretty much as the identity, but with a minus in between. So this will give us psi dagger with a plus, psi plus minus, psi minus dagger, psi minus. Okay? But in QFT, the fields are operators in a Fock space. And so the conserved quantity, we have to act in a particular state in this Fock space. And notice that these guys are the number operators of a particular state. So this will give us the number of spinors with positive chirality, and this will give us the spinors with negative chirality. So when acting, when the conserved quantity acts on a particular state in Fock space, this will give us the sum of the number of chiral spinors with chirality plus or with positive chirality plus the number of spinors with negative chirality. Okay? And in the other case, J, the temporal component of J5, when we act exactly with a state in our Fock state, we will see that something similar happens but with a minus here. So it is the difference between spinors with different chiralities. So when acting, on a particular state in Fock space, we conclude that the vectorial charge will give us n plus, plus, n minus, where n plus, as I was saying, is the number of spinors with positive chirality. And the other one, the same thing but with the negative chirality, okay? And for the axial charge, same thing but with a minus. So these two quantities are conserved at the classical level, but they don't need to be conserved at the quantum level due to anomalies, okay? And this is what I would like to explain, because the different computations to see this were performed by the people at the end of the 60s perturbatively, but I will do now the computation of Fujikawa, okay? Let's go. To do that, I will focus on the path integral formulation of quantum field theory.
Professor, why was it called the vectorial conserved charge?
All right, so it is vectorial because J nu, this guy transforms as a vector under parity transformations.
Okay.
So if you put this guy into a mirror, you will see that it transforms as a vector. But the other guy, the J mu 5, the axial current, transforms as a pseudo vector, like the angular momentum, for instance. The angular momentum is constructed out of the product of two vectors, the vector product of two vectors. So if you perform a transformations of the two, your vector will remain invariant, let's say, because it is a composed vector in a sense. Same thing here. So this is transforms as an axial vector under parity, and the other guy transforms as a vector. So this is why I call it the vector current and the axial current. Okay.
Thank you.
Any other question? Yeah.
About the charges vector and axial.
Yeah.
You mentioned that this form is because of the Bayes representation of this mode.
Right.
If I choose another representation, the form remains the same, or just another line form? Like, will I get the n plus n minus thing, or will I get another expression?
I think you shouldn't in general, but you cannot. Okay, if your spinors are massless, you can choose whatever representation you want, and then it can perform always change of basis in order to go to the Bayes basis. And even though perhaps choosing a different representation will give me a different result, and can always perform a change of basis in order to put the result in this form. If the spinors are massless. If they are massive, this is not a conserved quantity. So I hope I would have said this. If you consider the mass term into the Dirac-Lagrangian, the m psi dagger psi, and you use the axial transformation, you will see that your action does not remain invariant. So the mass term breaks the axial symmetry explicitly. So this is not a conserved quantity. But in the case of massless spinors, it is. And actually, if you consider the standard model, none of these spinors have masses until the Higgs boson acquires a vacuum expectation value. And only then they are massive. But before the spontaneous breaking of the gauge symmetry, in that case, your spinors are massless, and so this argument holds. Okay, what else? So let us compute the anomaly now. I'm doing with time. Okay, let's try. So I will consider now. There are some details about the similarities and differences with the vector U1 vector symmetry. I will skip that part for the sake of the time, but you can find this in my notes that I will send it to the organizers, and then you can check that part. But I will focus now on the axial symmetry only. So now the axial anomaly, okay? And for the axial anomaly, from here on, I will work in Euclidean signature. So I will perform the analytic continuation of the Lorentzian time into Euclidean time. The gamma matrices change in the following way. This E is for Euclidean, but I will avoid writing E every time. So from here on, these gamma matrices are Euclidean. And so if you take this and plug it into the Clifford algebra, now the Clifford algebra is this one. minus 2 times the delta. Okay? And this is all what I need. So consider the path integral for a Dirac Maxwell theory, also known as QED. And the path integral is integration over all paths. And for simplicity, I will neglect all the Fourier-Popov determinant and subtleties that you need to take into consideration when considering gauge fields. So I won't consider that, but you should bear in mind that there are in this functional, and this will be e to the minus. This will be the QED in the Euclidean plus sources, but they won't play any role in the computation, so I will just put it there symbolically. And the action in this case, in the Euclidean section, would be d for x plus 1 for f mu. And now this slash is gamma mu. And the covariant derivative for the U1 gauge connection. So this is the connection for the U1. Okay? And so there is a property, a very important property that the path integrals in general have. And since we are integrating over all fields, the path integral is invariant under field redefinitions. So I can perform whatever field redefinition I want, and the path integral will remain invariant. Even though the measure could be non-invariant, the action will not be invariant perhaps, but the whole thing has to be invariant. And this is a very important property that I will use from here on, because it allows us to derive conservation laws in a super simple way, but considering quantum effects. And these conservation laws in general, that consider the quantum corrections are known as the Ward-Takahashi identities. And you can derive it simply from the case, or simply by considering that the path integral is invariant under field redefinitions. And so, the path integral is invariant under field redefinitions. And this is because we are integrating over all fields. So if I change my fields at some point, the measure will take into account my new field, so it should remain invariant under field redefinitions. So if I take, for instance, for instance, take psi going to another one, call it u psi, and then I need to perform a transformation of the measure, a transformation of the action, but at the end of the day, the path integral should remain invariant. And so this transformation implies then this implies that the path integral with this new function that redefines my fields, let's call it in this way, should be equal of putting here just an identity, because it is invariant under field redefinitions. So I can choose a particular one, a particular field redefinition. Take a particular field redefinition. For instance, let us take a local U1 axial transformation. It is a particular one, so, but it is no longer global in this sense, it is local. At the end of the day, my path integral should remain invariant. So this should be beta x gamma 5. If this is the case, I can expand the left-hand side in powers of beta. And since this is a Lie loop, I can consider just at infinitesimal order the expansion up to linear terms in beta. Okay? And expand let's do it here. So the first one will give us 0, 1, and this is a functional, so we need to perform series expansions in a functional way. This will be d for x, then I beta x gamma 5 d zeta u x in d beta x, where beta x is equal to 0 plus blah 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 blah. Okay? What is important now is that since the path integral is invariant under field redefinitions, this implies that this guy has to be equal to this one. So for an arbitrary beta, this piece has to be 0. Okay?
The exponent doesn't change in the Euclidean.
Sorry?
In the Euclidean
Yeah.
coordinates, the exponential doesn't have a negative here.
Not in this case, because you can see that gamma 5 goes exactly to gamma 5, because gamma 5 is constructed out 4 gammas. Let me put it here. So gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3. And we are weak rotating each one individually, so gamma 5 will remain the same.
Okay. But it's the only one?
It is the only one. All the others will change by an I.
But why are you integrating? Yeah. Because the left hand side depends on S, and the right hand side doesn't depend on S.
You mean here?
Yeah.
Yeah, I'm just performing series expansion in terms of beta.
No, yeah, but the integral is not in the definition of the U. So where does the integral come from?
Okay, yeah. This is exactly because these are functional. So,
Okay.
and I have to integrate over all the space in this case.
So the x is in the integral, right?
Dx is in the, yeah, exactly, because,
In the boundary of the integral.
yeah,
Okay.
exactly.
But the integral should we rotate too, right?
Yeah. So this, actually, I will avoid putting E everywhere, but this has an E. So this is in Euclidean space. The integral is performing in Euclidean space. Okay? Yes.
We don't need the definition of gauge fields.
A redefinition of the gauge fields. You mean when I go to the Euclidean or?
Not to maintain the path integral invariant.
No, okay. No, in this case, I'm only rotating because this is not a gauge symmetry in general. So I do not have any gauge fields for this local symmetry. This is not a local symmetry. This is a field redefinition. So I'm not changing in this case the gauge fields, just the fermions. So I will leave invariant the gauge fields, I will change the spinors, and the path integral should remain the same because it is invariant under field redefinitions. Okay? And so what we learn from here is that then for an arbitrary beta, we have this relation. And this is super useful to derive the word Takahashi identities in general. For instance, consider how the Dirac-Lagrangian changes by this local field redefinition. How does it change? So let us take the Dirac-Lagrangian, not the Dirac, the QED-Lagrangian there. So the QED-Lagrangian, f mu remains invariant, and now we have this piece, but this piece, when I include a local U1 axial transformation, it doesn't remain invariant because I do not have any gauge field for the U1 axial transformation. This is not the case, for instance, if I would have considered the U1 vector transformation. In such a case, the action does remain invariant, but in the case of the axial one, it does not. So here it will give me QED prime that will be exactly the same piece, but you can integrate by parts because notice that here it will appear e to the I beta x gamma phi. On this piece, it will give you also a plus e to the e beta gamma phi. I have a gamma mu here. You need to commute them. And at the end of the day, you will have upon integration by parts, you will have something like this. There was a question.
Yeah. Then you wrote like one relationship only, right? Like the derivative with respect to beta is equal to 0.
Yes.
Yeah. But from that expansion, you have like an infinite number of relationships.
Right.
Does the higher order derivative give more information, or it always like gives.
No, it doesn't, because it will give you just, if you have this, in particular in this case, it will give you always derivatives evaluated at beta 0. It won't give you anything else. I'm not completely sure in other cases, so I will take a look at that. But in the case of the U1 axial, since it is a Lie group, all the information is related near to the identity, so I can work near to the identity and I have everything there. But in large transformations, I'm not completely sure. But in this case, since it is a Lie group, I can work near the identity and everything is fine. And so the action will change in this way. And notice, if we put there the transformation of the action, and I do this, if the fermionic measure wouldn't have transformed under U1 axial transformations, then you will see that equation, let's put it a star, if the fermionic measure would have been invariant, and this is exactly what happens, like in the U1 vector case, then equation star gives, so if you perform this transformation at the level of the Lagrangian, zeta u will be dA psi bar d psi e to the minus, this piece will give me I q e d e, and then I have an additional piece, so this will be plus, I will put an I in front, I have a d for x, and now I have this beta x d mu j mu 5. So this equation star, if I take the derivative with respect to the local parameter and then evaluate this at beta equal to 0, this will give me the set the beta will be the A, the psi bar, the psi, and then I will have mu 5, and this is it with an I probably, and then you take, and there is the exponential here, but then I will take beta equal to 0, so this piece now vanishes, and this is exactly the vacuum, and since this is equal to 0, this means that this guy, the integrand, has to be equal to 0. So this is the definition of the vacuum expectation value of this operator. Equal to 0. However, the fermionic measure in this case is not invariant. And this is the whole point of the Fujikawa computation. So I will put here, however, is not invariant. So this equality doesn't hold. So at the quantum level, this is not truly conserved. Okay? So I would like to give you some details, not that much because I won't have enough time, of how to compute the non-invariance of the fermionic measure under U1 axial transformations. And this is the source of the anomaly. Okay? But if you do this in the vectorial case, you will realize that the measure is invariant, and so the electric current, and it is of course related to the conservation of the electric charge, is conserved at the quantum level, but the axial one is not. Yes.
When you do the observable, you usually divide by the path integral.
Yes. Yes.
So
I'm neglecting all that normalization
Okay.
factors and blah blah blah.
But-
Yeah, you're right. So there is here n. Since these are fermionic, it doesn't go below; it goes above, and yeah, you need to divide by.
But it will cancel out, right? The measure, because the measure is a global thing that goes out of the path integral, right?
That's true if this is invariant. But if it is not invariant, it will contribute at the end. So in the case of the U1 case, of the U1,
Axial, right? You were axial, you mean?
the U1 vectorial, it will cancel out. But in the U1 axial, if you take the normalization factors and everything, it will contribute in any case.
And you will get additional terms in the one.
Yes. This is what I would like to do. Do not have enough time, but I will try to give you the main steps, and then you can follow my notes afterwards, okay? Any other question? Anyway.
In the zeta function, if I compute the zeta of the identity, I should get a number, a function, or I ask because in the next term you have an integral with a gamma phi.
Actually, okay, so in general, this is a function. It is an object that you take derivatives and gives you correlators in general. And so correlators are, you can interpret it as amplitudes or whatever. But this is a relation that holds between functionals. So it is integrals of functions in general.
The next term is a matrix.
This guy?
Yeah. No, the whole term.
Yeah. No, this is a functional as well. So it is a derivative with respect to a function of a functional, but it's integrated. It is like an smeared. It is smeared by this function here. So it has the correct units as well in this case. Okay. All right. So let us see how the fermionic measure transforms in this case. And to make sense of the fermionic measure, it is convenient to span the spinors in terms of eigenstates of the Dirac operator. So let us see how the fermionic measure transforms under local U1 axial field redefinitions. To do this, consider these guys, this set of states being the eigen states of the Dirac operator. So this means this slash acting on psi m will give us the eigenvalues of the Dirac operator. And span the Dirac spinors as this will be psi x sum over n Salud. So this is the expansion, and A and B are Grassmann numbers. And Breno gave a lot of details about Grassmann numbers, so you know what they are. Where A, M, and B and R Grassmann variables.
Cristóbal, there will be a bar, right? There? Instead of the dagger? Or is a dagger?
It is a bar.
No, at the left, at the spinner.
This is a dagger.
At the gamma 0 was happening.
It is included here.
Okay.
I will include everything in the B.
Okay.
Yeah. Thank you. And so since these are eigenstates, they satisfy some orthogonality conditions. And they are the standard ones: psi dagger m x, psi m x is delta m n, and in this case, let's say n x and y is equal to delta x y.
Professor?
Yes.
In this decomposition, the components of the eigensense are Grassmann variables as well?
These are not.
Okay.
These are just, let's say, complex functions, and the relation with the statistics of these guys are encoded in the Grassmann variables. But these are just complex functions that satisfy these funny relations. Okay, so what about the fermionic measure in this decomposition? So, in terms of the eigenstates, the measure reads. So let's take this part. So you know that this is the product of all the of the measure of all the possible fermions. So this will be, and since we are doing this decomposition, this will give you a Jacobian that can be written in terms of a determinant. But the determinant, since these are Grassmann variables, goes with a -1. I'm not sure whether Breno told you this, but you can check it in standard QFT books. But the idea is that this will give you a determinant coming from this guy that will be psi n dagger x to the -1, and this -1 is due to the fermionic nature of the Dirac spinors, and the determinant is coming just from the, let's say, sort of a change of variables here. This is the Jacobian. The other one will be psi m x to the -1, and here you have the product, let's say n b bar n, product m b a n, and using the standard, and these of course are operators in a Fock space. But if you use the relation that the product of two determinants is the determinant of the product, and they are operators, but to take the product you use this way of doing the product, and we know that these are orthogonal. So this will give you the determinant of a delta, and the determinant of a delta is equal to 1. So the measure in terms of the eigenstates looks like this. But I haven't performed any U1 axial redefinition yet. This is what I would like to do now. But first of all, we need to check how these Grassmann variables change under U1 axial field redefinitions. Okay? So the question is, how does A and B transform under U1 axial field redef? Let us see that. So let us take this and perform this local U1 axial field redefinition. But now I will use the decomposition in terms of the eigenstates. Okay? So I will expand up to linear order in beta, and then I will put here the decomposition. Okay? So this will be 1 plus I beta x gamma 5, and here psi n x. And so the idea is to redefine this as a n prime psi n x. And now, in order to see what a prime is, we use the orthogonality conditions, like the standard Fourier trick that you learn in using Griffiths in your first course of electrodynamics. So the idea is to integrate both sides, d for x, psi dagger m, x, and so you will have d for x psi dagger m 1 plus I beta x gamma 5 sum. I will put the sum here. Not that much, so the integral first, d for x, and the sum n. And here, alpha n psi n x, and this is it, and this is n, a prime, but I have the integral, so then we put the integral first. This will be d for x sum over n psi n target psi m, sorry, x a prime n psi n x, and this is it. So on the right hand side, I will use the first orthogonality condition, and we know that this will give me the delta, and so the delta will kill the sum, and on the right hand side I will have a prime m, and on the left, notice the first one will give me the delta and alpha m, and the other one will give me the integral psi dagger m beta x gamma 5 psi n x, okay, with the sum. So this can be written as the first will be delta, this will be sum n, this will be delta m n. I perform the integral in the first, this is a n, and the other one will be just the integral d for x, the sum n psi dagger n x, there is a beta that I will put here, and now in between I have the gamma 5 psi n x a n. So this can be, I will define now the sum in front, n, a matrix, let's say B M N A N, and this will be A M prime, where this matrix B M N is equal to the delta M N plus there is a, there is an I here, sorry, there is an I, I, D for X, beta X, sum, N, psi dagger, N, M, sorry, gamma 5, psi N of X. So this is the matrix. I'm running out of time. So the idea now, you do the same for the adjoint Dirac spinor. And I will put the result here. But this is the important result. This is the matrix whose determinant needs to be computed. But now we have I will put here how the psi dagger transform, dagger prime, that will be defined in this way as well. It will be sum over n, psi dagger n, b bar n prime. Same here with the Dirac spinor and with the A, but now A n prime will be sum over m b m n m, and for the b bar and prime, same thing. So this is the result. This is how the Grassmann variables change under U1 axial transformations. And notice, and this is the important thing, it doesn't go with b to the -1 or with b dagger. It goes exactly with the same b. And this has to do with the fact that when you change psi going psi bar going to psi bar prime has the same sign in the transformation. Okay? This is somehow translated into this condition. If you do the same for the U1 vector transformation, you will see that the A prime goes with the particular matrix here without the gamma 5, and in the other case it's exactly the same but with b to the -1. So when you compute how the fermionic measure change for the U1 vector transformation, these two guys will cancel. But this is not the case in the U1 axial transformation. So just to, how much time do I have? 1 minute. But I started late. Okay, but I will finish now. No, this is fine.
It shouldn't be a sum in the term. The BMN.
BMN. Here you mean?
Yeah, the sum.
I put it outside.
Yeah, but in the next step, the delta MN and the integral.
That is here?
Yeah, that's.
Ah, you're right. You're right. Thank you. No, it should. Just let me. I agree with my notes. Yeah, you're right. Thank you, Aniel. It shouldn't be the sum. Thank you.
Professor?
Yeah.
When you multiply the determinants and they cancel out, shouldn't there be a delta?
Yeah, and that delta will give you. Okay, erase that.
The
Yeah, there. It is like changing M and M in that case. So they will be equal. But the determinant of the delta is 1 at the end of the day. So you're taking the determinant of a matrix. This matrix is the delta. The delta is the identity, so the determinant is 1. Okay, so at the end of the day, the fermionic measure transforms as, and in this case, so you will have a determinant of this transformation matrix from each of these pieces, and so you will have two determinants, but they are the same, to the minus 1. So this is, it can be written in this way. So this is goes to prime to the minus 2. And this is what you need to compute. So just to give you some steps, we use the standard technique, like the determinant of B can be written as the exponential of the trace of the log of B. We expand, use that the log 1 plus x is like x when x is small, and there will be a trace here. And formally, the trace is divergent. Okay? So the determinant of B can be written in this way: exponential minus 2i d for x and gamma 5. And the sum over n is because we have the trace here. And in general, this guy is divergent. What Fujikawa did is to introduce a regulator. And he removed it at the end of the computation. And it was a gauge invariant regulator because it was constructed out of the eigenvalues of the Dirac operator. So this is divergent. And you need to regularize it. You can check my notes how to do that part. But once you introduce the regulator and you perform that sum in a correct way, the result is that this is we'll finish now. This is minus 1 over 16 pi squared f tilde f. And once you plug this here, take into account the non-trivial transformation of the fermionic measure into a Bath integral. You will get an additional piece when you perform the U1 axial field redefinition of your Bath integral. this is my last line. Then theta u x is dA dip psi bar dip psi e to the minus QED E. And then there is a piece coming from the non-invariance of the Lagrangian. There is another piece that comes from the non-invariance of the fermionic measure, and this is T for x, beta x, and these two pieces are here. 5 plus 1 over 8 pi squared f tilde minimum f mu. And so you take the derivative with respect to beta and then put beta equal to 0. And due to the invariance of the path integral under field redefinition, this should be 0. This implies, so you take this, and this has to be 0, and so this implies that the axial current is not conserved, but actually gives you this piece. So this is the main result of this talk. Fujikawa actually did this in Yang-Mills theory. People have done this in the case of gravity theories as well. And the result is that you will get the sum of all the Pontryagin densities if you extend this covariant derivative under the U1 gauge transformations to another gauge groups. You will get the sum of Pontryagin densities. And of course, if you integrate this, you will have a topological invariant on the right-hand side, which are non-trivial for instantons, monopoles, and different configurations with non-trivial topology. And the left-hand side, as I was saying, is the difference between the number of spinors with positive and negative chi-entities. Okay, sorry for the delay, but I hope that this has been helpful. Thank you.